So what is the image point of 2, -5 after translation right 4 units and up 3 units? Well, we know left and right is about the x-axis, which means that it's going to affect the x value in that ordered pair. So that is the preimage ordered pair, 2, -5. And right there, we just saw that it's going to go right 4 units with the x value. So we have two values, right? We got the x value, and then we're gonna apply that to the right 4 to the preimage, which will then give us the image values. And again, it will be an x value there as well. Okay, so to the right 4 units, to the right, at least for an x-axis, would be adding. So the 2 that is in the preimage, we're going to add 4 to that in order to get the new x value, which would then be 6 for the image. Then we have a y value that's -5, and we're going to do what it tells us to do in order to get the new y value in the image. And here it says that you're going to go up 3 units. So up, of course, is the y-axis, which means this is going to affect the y value. So the -5 up would be adding 3. So I take that -5 from the preimage, and I add 3 to that. So -5 plus 3. If you need a calculator for that, don't feel ashamed. It's not a big deal. But yes, we now have the image ordered pair. Here's our objective for the day. I can rotate and dilate points on figures. So take 15 seconds, copy this down, then we'll get started. All right. So to rotate, we're going to take a shape like, well, not really a star, but just shapes in general. And we're going to say we're going to rotate this, or maybe along this corner of this star here. But this would be considered what they call counterclockwise, or we can rotate it the other direction, which would be clockwise. Now you can do this with any number of degrees, but that would require a protractor, which we do not want to use today. So in 10th grade, it's probably likely that they will go over this, or maybe 11th grade. We don't have to worry about protractors today. All we got to do is spin the crap out of this thing, and then it will rotate. Now a dilation is just changing the size of a shape, but will be correspondingly similar to our preimage. Okay, so we've seen the slide already. A preimage is an object or shape that you start with, and then after we do something to it, and so far we've done 2 things to our figures or objects. We've done translations, which we saw on the bell work, and then we've done reflections, which we saw last lesson. So those are called transformations, and the two that we're going over today are still transformations, which is rotations and dilations. But after you've done something to the original shape, or the shape that you start with, that's when we get an image like this one. So the preimage is the shape that you start with, and then the image is the shape that you end with. Okay? And then we've seen this marking before. If we see this marking, which we will today, is what we call a prime mark. So if we look at original shapes, or shapes that we start with, the preimage, it will not have markings like this if it shows us a shape with points that are marked. So if we were to go back, and let's say we got some kind of rectangle like this one, and let's say that this was our preimage. So you know what, let's change this a little bit. Yeah, it'll be red to represent our preimage. And let's say that this preimage, we'll just look at the top left corner here. It could be labeled point A, all right? Well, if we were to take this shape, and let's say that we were to copy it, and again, let's just move it for now. So let's say I took this shape, and then I moved it to the right, and then up. Well, now what I have is a image, so we'll make this purple instead. And instead of it showing as point A there in the top left, it would now be A prime. Now the good news for us is that A and A prime will correspond to each other. And if there were more points on this, let's say that this was C right here, then its corresponding point on the purple image would be shown as C prime. But as it turns out, what we can do is you can actually take an image like this one, A prime, C prime rectangle, and let's say that you moved it again up and to the left like this. Well, if that were the case, it would have gone through two transformations, and you would see this as A prime prime and C prime prime. We won't see too much of this prime business between these two, but we will see at least one problem that has this prime stuff on it, okay? But again, they're not going to say, hey, this is your preimage, this is your image. They will tell you which one's the preimage and image through these prime marks or whether they don't have the prime marks. So, rotations, which is just taking a shape and spinning it, means that we're going to take the shape and spin it around some kind of central point of rotation, which the good news for us is the center of rotation will be the origin for all the problems today. Okay, so this is going to make some rules for us. So since we're rotating around the origin, this is why we no longer need a protractor for this type of problems, okay? And then everything moves around that point in a circle, that point, the center of rotation. But like we've seen in the past, in today's transformations, we're not going to rotate sides of the shapes. We're only going to rotate points, and then once we get the shape rotated, then we will connect the points. And then down here it says the size does not change. What that tells us is that rotations will also maintain congruence. Here's my congruent symbol. So we're not changing the size of the shape. We're not making it bigger or smaller. All we're doing is changing its orientation through some form of rotation. So rotating a full circle would be rotating in 360 degrees, which we should not see any rotations of 360 degrees. Because if you do, then you just end up at the same shape that you started with. So we should not expect to see this rotation. But today, and this is again why we know we do not need a protractor, is we're only rotating in multiples of 90 degrees. So 90 degrees, what does that mean? Well, if you were to take lines, which would of course be parts of shapes. So let's take this line right here. Well, let's make it diagonal, kind of like this. And then if it were to create a 90 degrees, and I'm not saying that's exact, but a 90-degree angle would be in this type of fashion. I guess it's like a T, like this. But it makes a 90-degree angle right here. Now, since we're only rotating in multiples of 90, like we see here, 90, 180, and 270, we don't actually need to measure this, which is why we're saying we don't need a protractor. Now, that would be 90 degrees right there. But if you think about this, if you were to go not just from the red line, but to the purple line and then back to the red line right there, you went 90 degrees first, and then you went 90 degrees again. 90 plus 90, that's where we get the 180 degrees. Now, I went in this direction, but you can see also that it wouldn't matter if you went in this direction. Either 180 degrees gets you in the same location, no matter which way that you rotate. And then, if we wanted to say, you know what, we're going to go 90 degrees, 180 degrees, and then another 90 degrees right there. It'd be 90, 180, and then this blue would be a total of 270 degrees right there. Okay, so this is important for us so that we can understand where this rotation is going to happen. But you'll notice as well that if I were to, because I went for the 270, I was going in this direction. But if I were to reverse the rotation, I could have gone just 90 degrees this way. Or to get 90 degrees, I would have gone 270 degrees the other direction. That will be important for us to remember, because of the rules that we're going to be seeing. And yes, you've only got two different types of rotations. You've got clockwise, which is good because the arrow's showing us which direction. And then you got counterclockwise, which is in this direction right here. But again, this will create rules for us, which if we can just know the rules, we don't need protractors, although they're fun to use if you're a math nerd like me. And you can do any rotation around any point, but today we're only rotating around the origin, and we're only rotating in multiples of 90 degrees. So is figure Z a rotation of figure Y? And then if it is a rotation, how many degrees and in which direction? So to figure out if it is a rotation, what we got to do is check all of the coordinating points from both the pre-image and the image and just see how many degrees they've been rotated. Because if they're all the same, then it definitely is a rotation. If not, then it would not be, okay? But at the top, it says figure Z is a rotation of figure Y. This means that you would start with figure Y, and the starting figure is always the pre-image. So we now know that figure Y is our pre-image, and really, by the process of elimination, now we also know that figure Z is the image. So we have the pre-image, and that means we now know the image is figure Z, or it's the figure that you end with, the image. So we have the two shapes. I don't care about the shapes. All I care about are the ordered pairs on the shapes, meaning that I would want to compare maybe this point with this one right there, because they are corresponding points of the two triangles. I can see that I get from this line and this line, I get a right angle there, and this line and this line. So that point has to correspond to each other. Now, if it's not so obvious which other points correspond to each other, we can kind of show that. Again, we're expecting some kind of rotation. So that means if I were to look at this point, it would correspond with this top point. Again, the orientation has changed, so we have to be aware of that. And then finally, we've got this point and this point. Now, they're not labeled. So again, they did not tell us through the labeling of the two figures which one was the pre-image and which one was the image. If it did, then it would have to say maybe this is A prime, B prime, C prime, something like that. But they didn't. So this is what we're stuck with, but I can now see just through the colors which points correspond to each other. And we also know that all of our rotations for today should be going through the origin, which is right here, right in the middle, 0, 0 ordered pair. Okay, so what I'm going to do is I'm going to figure out how much rotation has occurred between, I'm going to start with the red points, kind of because they're close together. Now again, we don't need to measure these angles, we just need to know that it's going to be in increments of 90 degrees. So to figure out the angle, I'm going to go from my pre-image point, which is the red, then I go to my center of rotation, which is the origin, and then I go to the corresponding image point, which is in red as well. So I get this line here in blue, and then this line right here in blue as well. And we can see that that has to be a 90-degree angle. And you can see this is kind of like a larger right angle mark if you were to look at the grid as well. Yeah, that is definitely a 90-degree angle, so long as I'm rotating in this way. Okay, which I will plan to do. So this right here is a 90-degree rotation. Well, if that's the case, then all of the points should be rotated at 90 degrees. Now again, we don't have to guess, we don't actually have to measure the angles. If it looks like 90 degrees, then we will say that it is 90 degrees. So now I will connect, I'll do the purple points. So again, I take the original pre-image purple point, connect it with the center of rotation, and then I connect the center of rotation with the new image point. And yes, this looks like it is also. It's going to look a little sloppy now that I'm putting an extra angle in there. That's 90 degrees there. And then the green points follow along the same line as the red ones. So we get this angle, but we already have that angle marked. So all 3 points have been rotated 90 degrees going in this direction, at least the way that I have it. And that direction right there, just based on the last slide, that would be counterclockwise. Okay, but again, how many degrees was it? Well, it should have been 90 degrees because we have our 90-degree angle marks. But again, whether we have to mark those or not shouldn't matter. We don't need to measure those to see that they're exactly 90 degrees. All we got to do is see that it has to be in 90-degree increments. Okay. Now that's 90 degrees counterclockwise, but it's possible that if you wanted to, you could have gone the other direction, which would have taken a little bit more rotation, and you could have gone instead clockwise. Like we explained on that last slide. Okay, so if it's not 90 degrees, let's say we wanted to go in this direction. Okay, well then, let's use the lines on the axis there. So I would have gone in that direction. I would have had to have gone 90 degrees. There's 90. Another 90 is 180, and then another 90 makes that 270 degrees clockwise. All right, so we know that it is a rotation. If it is a rotation, how many degrees and in which direction? Well, it doesn't matter which one of these you choose, 90 degrees clockwise or counterclockwise, both will work. So I'm going to circle both, and it doesn't matter which one you choose. But yes, this is definitely some kind of rotation. If it was 180 degrees, we'd end up with is maybe this, the image would be somewhere in this area. But again, you'd say you'd connect the preimage point to the center of rotation, and then its image point, but then you'd see it's a straight line, which is what 180 degrees is. It's a straight line. It brings us to this slide. So that last one, we were looking at 90 degrees counterclockwise and 270 degrees clockwise rotations. This is an abstract form of the rule because, as it turns out, we don't actually need the graph, which means if we just knew the ordered pairs of the points, that we could use these rules, okay? So right at the top here, 90 degrees counterclockwise and 270 degrees clockwise. You're going to take your x and y value. You're going to switch the order, so now your y value becomes your new x value, and your x value becomes your new y value, but you make the y, this y, when you flip it here, you make it a negative, or opposite, okay? So this is not telling us that all of our 90-degree counterclockwise rotation or 270 degrees clockwise rotations will make this value negative. It's just saying that it's the opposite. So I have to keep that in mind. The negative just means opposite. So, for example, if we were to have an ordered pair, like this one, we'll just say -1, 2, like this. So this would be the pre-image ordered pair. And if it goes through either a 270 degrees clockwise or 90-degree counterclockwise rotation, then what I would do is I would take this y value here, 2, and now it becomes the new x value. But where this 2 was positive, its new value, 2 for the x, becomes a negative. So I take the opposite of that 2. And then the x value, which used to be -1 here, now becomes, it's still -1, but it is the y value, okay? So this would be the ordered pair of the 90 degrees counterclockwise or 270 degree clockwise rotation of -1, 2. Okay, but again, I don't really need a graph in order to do that. Next up, we have 180 degree rotations, and like I was saying, 180 degrees, since it creates a straight line with the preimage point and the center of rotation, it doesn't matter which direction you rotate with 180 degrees. You can go clockwise or counterclockwise. This rule will stay the same. So we notice we have an x and a y value, whatever these are. These would be numbers. But whatever they are after the rotation of 180 degrees in either direction, you're just going to take the opposites of both values. So, for example, let's look at some new values here. So if I had the ordered pair, it's a, we'll say 4, -7. That's from my preimage. If it goes through a 180-degree rotation in either direction, what I'm going to do is I'm going to keep the x value 4 in the x location. But again, this minus sign, or the negative sign, means I got to take the opposite. So where this used to be a +4, after the rotation it would become a -4. Again, it's the opposite. So if I look at the -7 y value here, which is negative, I would have a 7 value here for my y, but the opposite of -7 would be a +7. So this would be the new image ordered pair after 180-degree rotation of the original preimage point of 4, -7. And then this last one, rotating 270 degrees counterclockwise and 90 degrees clockwise. Notice it just kind of switched these two. It does work a little differently though, so your x and y values, you're going to have your y become the x, but now the opposite is with the x, which is switched to the y value, which sounds kind of confusing. But again, you have to pay attention to if it's counterclockwise or clockwise, or clockwise or counterclockwise. So let's do an example here with these. So we'll start with the ordered pair. We'll say -5 and 9, like this. Okay, so that would be our preimage ordered pair. And after either a 270-degree counterclockwise rotation or 90-degree clockwise rotation, which is exactly the same, we would take this x value of -5, and it now becomes the y value, but it's opposite. So where this one was -5, now we're going to take the opposite of that value as the y, the new y value, but it's now +5. And then the y value, where in the preimage it was 9, it's going to just stay 9, but become the new x value like this. So as much as you guys wanted to use protractors, we don't need them for this stuff because we're going to be using the rules. And these rules of rotation apply specifically as long as we are rotating around the origin. So this year, that's all we're doing for 9th grade rotation stuff. But in 10th grade, it's likely that they will now change the center of rotation. But for us, our center of rotation will be at the origin. All right, so this problem, let's look at our rotations here. And let's look at the rule because we know this is 270 degrees clockwise and 90 degree counterclockwise. Okay, and let's compare the points that correspond with each other. So I'm going to start with the red one. So our preimage ordered pair, there would have been at 0, -1. And then the image ordered pair would have been at 1, 0, like this. Okay, now does that work for this rule? Because we know it's a 90 degree clockwise, counterclockwise and 270 degree clockwise. Well, the original ordered pair at 0, -1 became the ordered pair 1, 0. Well, again, they switched the order, so now it's, instead of xy, it's yx, and then the y, we took the opposite. Well, it used to be -1, now it's +1, okay? So again, you can just apply the rule so long as you know the ordered pairs for each point. And then in purple, the original purple ordered pair was at 4, -1, and then the image was at 1, 4. So again, between these two, we had the preimage ordered pair at 4, -1, and then we had the image at 1, 4. So did that work? Well, again, we had the ordered pair xy, we switched the values, but we took the opposite of the y, so instead of it being -1, it was +1. And then finally the green ordered pair, which in the preimage would have been at 0, -4, and then the image was at 4, 0. So did that one work? Well, again, we start with an ordered pair of 0, -4. And then after the transformation, which in this case is a 90-degree counterclockwise or 270-degree clockwise rotation, well, we did take the values and switch them, but we took the y value, which was -4, and made it a +4 instead. So yeah, this rule works for all 4 points, which means it will work. I said 4 points, I meant 3 points. It will work for any ordered pairs that you find on any graph. Okay, so this one, it says you got an image of the point. We want to find the image of the point -7, -9. This tells us then that -7, -9 is the preimage ordered pair. Okay, so this is the value that we're starting with. And then it's going to undergo some kind of transformation, in this case a rotation, 90 degrees clockwise. So we're using this rule about the origin. And yes, it does have to be about the origin. It will say always it's about the origin because that's all we're dealing with today. But we start with that preimage ordered pair. So that's going to be at the ordered pair. We got -7 and -9. And after this rotation, it should switch the order of the two ordered pairs, of the ordered pair values. So instead of the -9 being a y, it's now an x. Instead of the 7 being an x, it's now a y. Now let's see what happens to the signs, right? So the x, of course, is just going to stay an x. So where the x was a -7, it will stay -7. And then the y is going to be the opposite. So where this used to be negative, it will now be positive. And this would represent the ordered pair for the image. This one's going to use the same ordered pair. So what is the image of the point -7, -9? But now the rotation is different. It's now a 180-degree clockwise rotation about the origin, which is good to know. Okay, so there's our rule. We know that the x and y will stay in the same location, but all we're going to do is take the opposites of these, which is y. We have the negative signs there. Again, it doesn't mean that they're always going to be negative. It just means that we're going to take the opposites of the x and y ordered pairs. So, where our ordered pair right now, we're going to start with an ordered pair where the x value is -7 again, and the y value is -9 again. It's going to undergo the transformation of a 180-degree rotation. And notice I do not care that it's clockwise because counterclockwise puts me in the same location. We keep the values where they are, so the 7 as the x, and then the 9 as the y, but we just changed the sign. So where this was -7, it's now +7. Where this was -9, it's now +9. So where we have the image, or the pre-image, at -7, -9, we've just found the image ordered pair of 7, 9. Like, let's say that this -9, let's say it was +9. Okay, then that just changes the sign over here for the image as -9. So this was positive, this would have been negative. And we're just changing the signs in these, not really the locations like we do for 90-degree or 270-degree rotations. So similar shapes is when we take a shape and we change the size of the shape, usually. Technically, congruent shapes are still similar, but by a factor of 1. But similar shapes is usually where we change the size. Now, what this means is that we see this old 7th grade word of proportional, which I think it goes back to 6th grade as well. Unfortunately, we don't remember jack squat from 7th grade, probably not 6th grade either. So, proportional just means that if you were to take the side lengths of the shapes, then you would get, and compare them, you would get proportional values, meaning you'd have equal fractions. So you could have something like 1/2 and 2/4, or 3/6, or 4/8, and so forth, okay? So that's what proportional means. The good news for us is today we're not dealing with proportionality. All we're dealing with is, because that's sides of the shapes, we're not comparing sides of the shapes. All we're comparing is the points of the shapes instead. Okay, but similar shapes will occur after this was part of the second, this is the second part of our objective. This is with dilations. So if it says to dilate, then we would expect the shapes to be similar and not congruent. So far, we've gone over 3 different transformations And that is where we get congruence of shapes. So that was translations. Translations. Then we did reflections. Then we did just barely rotations. Okay, so we got translations, reflections, and rotations. These will all keep the shape the same size, but it may change the orientation, at least these two will. And then translations really just changes where it is on the graph. Okay, so those are our 4 types of transformations that we've gone over in this unit. Today we're only going over 1 each. Next time what we're going to do is combine these. So you may go through like a translation, then a dilation. Maybe a reflection, then a dilation, or a rotation and a translation. Who knows? But for today we're just doing 1 at a time. But again, congruence means we got the same shape and the same size, meaning all angles are the same. All side lengths that correspond to each other are the same as well. So corresponding side lengths, again, we should be able to compare those on the shapes. But sometimes they're kind of funky, and there really is no expectation that you guys use this use the Pythagorean theorem, which, I don't know, in 8th grade is kind of a swear word. But now, you could use it, but I'm not gonna do that. Okay. So it's the same part of separate figures. So if I were to take, let's go back to the trapezoid thing like this. If I were to take this trapezoid, and let's say that I were to move it here, but let's say also that I were to make it, a little bit bigger like this, so I've enlarged it, right? Okay, well, now I have 2 different shapes. They're definitely not congruent because one's much bigger than the other. But you can compare corresponding sides like we did before on the triangle congruence statement. So if I were to look at these sides, well, they wouldn't be the same, but I can color code them and say the red sides correspond with each other, because I would call this the top of the trapezoid, and then or you could say, well, I got the bottom side as well. Okay, the bottoms are corresponding. Now again, are they congruent? No, we don't have the markings to prove they are congruent. But then I would maybe have this orange side right here, and those 2 orange sides, again, they are similar and they are corresponding, but they are not congruent. I'll just keep these ones green, okay? So this shape, the original shape, the trapezoid, and then its enlargement have corresponding side lengths. What I can do is I can create proportions, because I'm a math nerd, with these values and then see if they actually are equal. And if they were, then I would say that they are definitely some kind of dilation of each other. They're similar. So size of figures may change, just like we see here, but side lengths can still be corresponding, just like we've color-coded. Orientation will change if dilations are combined with reflections or rotations, which we may see. So you may see like an enlargement of this one, but they may like rotate it. Or I wouldn't say, well, maybe they would reflect it down or something like that. So a dilation, again, is just what we saw in that last slide. We took a trapezoid and then we made it bigger. And so we had similar figures. We had similar figures, not congruent figures. So dilations will not usually maintain congruency, but it will maintain similarity instead. So all corresponding side lengths are proportional by some kind of scale factor. So this should go back, I think this goes back into 6th grade, maybe 5th grade, this word factor, but unfortunately most elementary teachers are not familiar with this word factor. A factor is a value that's being multiplied by another value. So you can have 2 factors being multiplied by each other in order to get a product. What this means is that when we see the word factor, we should expect some form of multiplication. And that's what we're doing with dilations, pretty much. We're almost always using multiplication. Now, if I were to take multiplying by some kind of proper fraction, which is a fraction that has a value less than 1, it would shrink the object. If I multiply by a scale factor that's more than 1, then we would expect the shape to get bigger. Now, we don't really care about that, because all we're going to be doing is worrying about points on the graph, not actual side lengths. So where it says that it's proportional, we don't care about that because that's for side lengths. What we are worried about is the scale factor, which not only applies to side lengths of shapes, but also now, like we will see, to ordered pairs in the shape as well. So we'll be dilating with the center at the origin. All it says right here at the bottom, that's all we're going to do, is multiply the ordered pair by a scale factor. Okay, so scale factors are usually represented by the letter K, and I don't know why that is, even though I'm a math nerd, but I also don't care. That means that the rule for dilations with ordered pairs, so if you have an X value and a Y value from, this would be the preimage, and then it undergoes some kind of dilation transformation, which we will be seeing today. Okay, then you will have to know the scale factor, K, and all we're going to do is we're going to keep the X where it is and the Y where it is, but I'm going to take those and multiply them by a scale factor K. And this will give me the new image. Now that's a way to look at it as a rule, which is abstract, but I also assume we don't care. Okay. Again, once we see this as an example with whatever scale factor it gives us, then all we're doing is multiplying X and Y's by the same scale factor. That will scale the point for us, which in turn also scales the side lengths for us too. All right here we have two triangles. I got the big one, triangle A, B, C. And then down here in the middle, I have the smaller triangle, A prime, B prime, C prime. The prime marks are what tell us that this smaller triangle here in the middle is the image, meaning it's the shape after it's undergone some kind of transformation. Since the size has changed, we do know that this is some kind of dilation. Right? We took something big and then we made it smaller. This also means that since we made it smaller, we're expecting the scale factor to be less than 1. Now the question just says, are they similar to each other, or in other words, are they dilations of each other? It's not asking for the scale factor, but we're going to find it anyways. So I'm going to start with my ordered pairs that correspond with each other, and we know that the letters correspond with each other. It's just, for example, A up here at the top is from the preimage because it doesn't have the prime mark, and then A prime has to correspond with it because it's the same letter but with a prime mark, and the prime tells us that it's part of the image. So let's look at the ordered pair for A. So that appears to be at 0, 9. And then A prime appears to be at 0, 3 instead. Now, if this is a dilation, we'll have to multiply all of the original ordered pairs from the preimage by the same value. And right here, we could say, well, 0, 9 to get to 0, 3, what would I multiply these values by to get the other ones? And that may not be so obvious. So let's look at the ordered pairs for B. Okay, so B right here, this appears to be at 6, negative 6. And then B prime appears to be at 2, negative 2. Okay, well, the second, I think the B's are a little bit more clear. Let's compare the C's as well, which we will do, which appears to be at negative 6, negative 3 from the preimage, and then the image has ordered pairs at negative 2, negative 1. Now that may be obvious. Some students say, well, I know that we're multiplying by 3. That would be true if you're going from the image to the preimage, right? If we started with a small one and made it bigger. But going in the backwards direction, instead of multiplying by 3, because I can't multiply 9 by 3 to get 3, that'd be 9 times 3 would be 27. What I can do instead is I can take the 9 from my preimage, and what I would do is I would multiply it by 1/3. And that will give me the image value of 3. Now, will that work for 0 as well? Sure it will. Anything times 0, including 1/3, is still going to be 0. Okay, so I can see from the A value, I multiplied the ordered pair by 1/3 in order to get the image ordered pair of 0, 3. Now I should have to do it for all the ordered pairs. So for the next one, I'll take the 6 there and multiply it by 1/3. And if that works, I should get 2, and I do. So I'm going to do the same thing with negative 6, multiply that by 1/3. What do I get? Negative 2. Yeah, that works. So right now it looks like these definitely are a dilation, and actually that's all the work we would need, but I'm going to do more because this is so fun. So if I were to take that negative 6 in green and multiply it by 1/3, I would get negative 2. And if I were to multiply the negative 3 by 1/3, I would get negative 1 as well. Since all of the ordered pairs are being multiplied by the same 1/3 in order to get the image ordered pairs, that means this definitely is a dilation. And in addition to that, we found the scale factor of 1/3. Now again, it did not ask for the scale factor, but we found it anyways in order to determine if this was some kind of dilation. Now something else that you may find interesting, which I doubt you will, but since I'm a math nerd, here we go, is if you were to connect the center of rotation, not the rotation, but the center of dilation here, which is the origin, and you connect the points, okay, you should find that all the points, if you were to connect them, go through that center of origin. So if I were to connect the red points, up here right through the middle, see how they go through the same point, and even the green points, boom, from the center of dilation through the points, these all go through the same center of dilation, which should be the case. Okay, now this one, like I was saying before, just the way it sets up, we made something big into something small, so we multiplied by proper fractional values. If we were to start with a smaller triangle and make it bigger, we would have multiplied just by 3. Now some students, instead of saying multiplying by 1/3, they would rather say I take 9 and divide it by 3, and that's fine as well, as long as you understand that it makes the scale factor 1/3 and not just divide by 3. I mean, they're the same thing, but factor indicates that you have to multiply by this value. This next one, so if you're not sure how I got this 1/3, again, you take a ending value, the image value, and divide it by the preimage value. 3 divided by 9 is 1/3 if you change it into a fraction. Of course, the zeros aren't going to help us, but these one would work too. Negative 1 divided by negative 3 is 1/3. Negative 2 divided by negative 6, also 1/3. Boom. So the figure below is dilated with the center of dilation at the origin. That's good. Almost all of our transformations are taking place around the origin. And this one has a scale factor of 1/2. Okay, so 1/2 means that it's going to take this shape and it should cut the size in half. But again, we're not comparing the sizes. Even though this has 5 points, and you can do all 5 points if you'd like, the question says, what are the coordinates of the image of point E after this transformation? Meaning, we only need to look at point E. The whole shape right there is really irrelevant to us because it's not asking for us to dilate the full shape. So we look at point E right here. Its ordered pair, so I see the x is at 2. So from the origin, it's to the right 2 and then down 6. So this would give me an ordered pair of to the right 2 and then down 6. X is 2, y is negative 6. But it says it's gonna undergo a scale factor of 1/2. So that again, factor indicates that we're going to be multiplying all of the ordered pair to negative 6 by 1/2. And again, you could do all of them if you'd like. So I'm going to take the ordered pair to negative 6, x and y value, and this should give me a new ordered pair after the dilation for an x and y value. So we got the 2, we're going to multiply it by 1/2. 2 times 1/2, that's a new x value that's 1 after the dilation. And then the y value as well, negative 6, we're going to multiply that by 1/2, and that would give me negative 3. So the dilated point from the origin will be at 1, negative 3, boom, right there. So that, I'm going to call it E prime. And we already have the ordered pair at 1, negative 3. I'll even label it right here, E prime. And this right here represents the image of point E. Now that's a little redundant because we put the prime mark with the E, and then we said it was an image. just to emphasize this while we get used to it. That's it. So this one, what is the image of 9, negative 4? It's the image of that, which means 9, negative 4 is not the actual image. 9, negative 4 is the pre-image. So that's the value that we start with, the ordered pair that we start with. But it's going to undergo a transformation, a dilation with a scale factor of 5. And again, scale factor, just the word factor itself indicates that we're going to multiply. Okay, not just one of the values, but the whole ordered pair of 9, negative 4. So we're going to start with this ordered pair of 9 and negative 4. And it's going to undergo a dilation with a scale factor of 5. So with that scale factor of 5, that means we'd take 9 and multiply it by 5. And again, there's no expectation that you do this in your head, or that you stack and multiply, or even that you use your fingers. Just push 9 times 5 in the calculator. Boom, 45. That's my new x value. And notice, by multiplying it by a scale factor bigger than 1, I did get a bigger overall value, which should happen with the next one as well. Negative 4 times 5, which would be negative 20. Well, we knew the pre-image, we just found the image. Bam. Okay, there it is, rotations and dilations. So rotating, again, only in 90-degree increments, 90, 180, and 270 degrees, clockwise or counterclockwise, and then dilations, of course, change the size of the shape, bigger or smaller, depending on what the scale factor. But we're just focused on points, which is why the objective is specifically about points. If you dilate, you're just multiplying the ordered pairs in the points by a specific scale factor, which we can find if we need to as well.